I'm going to talk to you about moderately hard functions, which are not so much of a new thing in cryptography, but a newly interesting thing. So first, I need to let you know what I mean by saying moderately hard. So when we think about cryptography, we think about things like encryption, when people can communicate secretly, digital signatures, that allow us to basically sign in the digital world, or hashing, where we create pseudo-random fingerprints for messages. Oh, and all of these systems are based on what we could say are hard functions. Hard in what sense? That breaking them should be practically impossible. So in order to achieve this, either we go for some number theoretic problems like factorization and discrete logarithms that they've been studied for a very long time, and we don't have efficient algorithms for them, at least not classically. Or we could go for average case NP-hard problems like shortest lattice vectors or decoding random linear codes. In the case of symmetric cryptography, it is like less straightforward. But in many cases, symmetric protocols are smartly iterated permutations, and finding the secret key is also very hard giving a message, even if you know how it works. Oh, but then what's moderately hard? There's a couple examples from the 90s, both time-lock cryptography and proof of work. These are functions that can be solved. They just take a lot of effort, a lot of work, and that can mean many different things. So let's go to time-lock puzzles. The idea is quite simple. The challenger chooses two primes, multiplies them to get an n, and then completely separate takes a message and encrypts it in their favorite way. And then they choose a random a in set n, and they compute a to the t mod n for a sufficiently large t. Now, how large? Well, this t is gonna kind of determine how much time should pass before this problem is solved. And then they encrypt this message. They release the key plus the C that they computed, as well as the other parameters. So if someone wants to decrypt the message, what do? Well, they just solve the same equation. So a to the 2 to the t modulo n, adds it to k plus c to recover the key, and then they use key to decrypt the message. This feels that it's kind of the same, but the important part is how they compute this number. So for the challenger, it's easy because they know the factorization of n, so then they can find phi of n. So first they compute the exponent, they compute 2t modulo phi of n, and then they compute a to the eth power. The solver doesn't have this advantage. So the best way that they can achieve this is by squaring a, and then squaring that, and then continuing that t times up until they finally get 80. So in this way, the challenger can create a puzzle that is easy for them to generate it, but that the solver is gonna need to spend some actual clock time to be able to solve it. It's a fun example. It's a pretty game, but it's not particularly useful. But not all moderately hard functions look the same. And another example are proofs of work. So these were originally conceived to help with spam. And the idea is that you have a target T, a hash function H, and a method gem. And the challenge is to find a bit string R such that the hash of your message and this bit string is less than this target. And by less, I mean you can take a hash and you can take the number that hash represents. So if H is cryptographically secure, the only way to do this is through brute force, which means we can expect that it will take t over 2n iterations of this hash until you find something new. In contrast to the previous one, this one is highly parallelizable. So we have these two examples. They both appeared in the 90s. They're very different to what we're used to in cryptography. And one of them is kind of a cute game. The other one didn't really fulfill its purpose. So it's something that was kind of forgotten. And then in 2009, Bitcoin appears. The basic idea of Bitcoin is that it's this ledger maintained by a group of people that is unpermissioned. And by that, I mean that people can join, people can leave. There's no central authority checking who can join and who can participate in the protocol. These systems struggle generally with people pretending that they are more people than they are. And the way Bitcoin prevents this is using proof of work. So the idea is that you can only participate as much as you contribute to the proof of work. And the important thing about Bitcoin is that it achieves state machine replication. And this is a big result. This is something that distributed systems people have worked for many years. And it is able to do this in this novel way because it is not impossible to disrupt. It is possible and you can break it. It just requires a lot of work and in practice a very high cost, which is the spirit of these moderately hard functions, which is not surprising considering it is based on one. So the basic idea is that Bitcoin is a chain of blocks of transactions. And for this chain to grow, users must create a block that is a valid proof of work and then add it. Which means that if you would want to rewrite some part of the chain, you would need to find a new proof of work, not only for each block that you changed, but also to all the blocks that follow as they are linked. And the way it works, the parameters are tuned such that a block will be created every 10 minutes. Which basically means Bitcoin is a timestamp server beyond also doing state machine replication. It is an environmentally catastrophic and incredibly expensive timestamp server, but it is that. But more importantly, it opened this new setting. Now we have new assumptions because we have a minimal setup. Generally in cryptography, especially for multi-parties, you need to know who's participating in the protocol. And that's not the case here. You have new goals because you have public verifiability, or you require that. And you have not so much new primitives, but like newly relevant primitives, like moderately hard functions or non-interactive zero knowledge proofs. So what I set out to do with Mark Stavens and Christian Schaffner was to take advantage of these moderately hard functions to try and do something similar to Bitcoin in the sense of timestamping without it being so expensive. So a bit of background of timestamping. It was first achieved by Aaron Sornetta in '91. Most protocols are based on hash chains, which actually was the inspiration for Bitcoin. But an important factor is that they require online verification. So you always need to either contact a trusted party or a bulletin board in order to check whether something is properly timestamped. Also, what that means, you have two flavors of timestamping: backdating and postdating security. The one that we care about is backdating, which means that we protect against an adversary pretending something is older than it is. The one problem is that there is an impossibility result for non-interactive timestamping, which is based on simulating an honest prover. However, we are in a new setting, or at least that's what I've been telling you. And in this setting, simulating other parties isn't easy. It takes effort, it takes work. And actually, we prove that this non-interactive timestamping is achievable using a moderately hard function. The function that we used are verifiable delay functions, which are effectively inverted time lock puzzles. Basically, the prover needs to take the t-sequential steps to output the result, and they also output a proof that allows for quick verification. And we also use a hash chain design. So if you want timestamp C, you hash it, then you start running a VDF over it, and when you get a new thing to timestamp, you add it to the chain next to the VDF, you hash that, and you run the VDF again. And when you want a timestamp, you take all of this and you have a timestamp that encodes T1 plus T2. And we proved well that this system is secure given certain limitations on how fast the adversary can compute these proofs. So in conclusion, we have a new frontier in cryptography. We have a lot of new different problems to deal with. We have a lot more primitives, but we also have to learn how to deal with them effectively. And one of the examples that we did is by creating this timestamping service. Thank you.
Thanks a lot, Esteban. There have been some questions in the chat, but some smart people have also been answering questions in the chat. Okay. So let me pick one of them, and hopefully you can also answer the question then. So okay. Samarth says, so it is not based on some popular conventionally accepted difficulty assumption like the decision of Diffie-Hellman. I'm not sure what the question was originally about, but maybe you already understand, Esteban?
Yeah, so the difficulty assumption here is that the fastest way to compute an exponentiation is through squaring, through iterated squaring. So this is something, again, that you cannot connect directly to a problem, but in all the study that has been done on how to efficiently do this, squaring is the fastest way to do this. So, of course, squaring, you can do, I guess, some lower level things to make it faster. But yes, you have these limitations.
All right, so there's one more question. Samar says, I was wondering if people have derived difficulty reductions or related time lock to other hard problems, he says.
So the problem with reductions in this setting is that in the end you have to take into account of the real world. Because you have to worry about processors and those kind of things. So we know that, for example, this VDF, we can reduce its difficulty to discrete logarithm under certain conditions. but the reductions are generally not as clean cut as you would have in like regular crypto.